Hello, this is Tom Bird, and this is the second of two presentations that I was to give at the Spring Science Sharing in late April, but I was called to a fire, so I wasn't able to present that day. So I've just now been able to record this one. This is on soundings as it relates to convective weather, so hope you find this worth your time. And what presentation in meteorology would be complete without a little bit of math, right? It'd make Dave Nolan proud, former meteorologist here in the office. And of course, here you see, some equations for CAPE and omega and updrafts and stuff like that, helicity. And this is about as far as we're going to take it. So you can breathe a sigh of relief as we move beyond this one. Now let's talk about the Skew T itself. And like a lot of presentations, this is going to be a 101 kind of thing for the most part, kind of introductory, kind of, base level. Really helpful for those that are just now new, getting into the Weather Service and getting their degrees behind them and starting their career in meteorology and weather forecasting. For some of us, this will be a lot of review. So when we talk about the Skew T or the sounding, why is it called the Skew T? Well, the answer is because the temperature lines on the chart are skewed. They used to be straight up and down. It was called the Stuvey diagram back then. But in 1947, they began drawing them at a 45-degree angle from the bottom. And what this does is it makes the dry adiabats cross the temperature lines at about 90 degrees and the moist adiabats at about 45 degrees. It makes the chart easier to read. So you can see there the temperature line there is skewed. And if you look at, it's called the Skew T log P. And the reason it's called the log P is because we've got a logarithmic function of pressure as you move from the Earth's surface aloft. As 100 millibars is a lot closer together down low than it is up high in the atmosphere, just based on the weight of the atmosphere and gravity. And so this is what the old Stuveys looked like. And you can see here on this chart, the temperature lines were straight up and down. They weren't skewed at all. So that's what they used to look like. And supposedly, with them skewed now at 45 degrees angle, it's a lot easier to see. So when we're looking at a sounding, exactly what are we looking at? Well, there's three pieces of information that make up the sounding that we release from our office every day. The first one would be the thermal profile there in the red, the temperature basically. And looking at that, we can get an idea of the stability of the atmosphere. And we can see the lapse rates, which is the change in temperature with height. The second thing that we easily can see from these are the moisture profile, where the moisture is, where it isn't, how deep it is, how dry it is, that kind of stuff. And then the third thing that we get is the wind profile from the Earth's surface up to the top of the sounding, giving us the speeds and the direction. So that's what we're looking at when we see a sounding. The question now is why we use them, and that would be what are we looking for now? And looking at those same three elements. Of course, when you're looking at the temperature profiles, you're looking at buoyancy or the lack of it, so stability or instability. So we're looking at whether or not the atmosphere promotes or resists rising motions in the atmosphere. Now, the next thing we look at with the wind profile there is shear, changes in direction and speed with the winds, with height. And that helps us to see what kind of organization we might get if we have storm development on any particular day. And then finally, of course, you need the fuel, which is the moisture. And so looking at the dew point trace, you get a good idea of whether there's the availability of fuel and what the distribution of it may be. So on those charts, there are a plethora of different lines across those charts. Some of those are the isotherms, some of those are the dry adiabats, there's the moist adiabats, and then there's the mixing ratio, and there's other lines also. So just take a second, maybe pause the video, and see if you can identify each one of those highlighted lines in each one of those four charts. All right, so here's where they are. The ones on the far left, those would be the dry adiabats. That's when a parcel's moving up from the Earth's surface, it's cooling along those lines if it has not been saturated. Second, there is the moist adiabats, and that's what a parcel would cool at as it moves away or moves upward in the atmosphere if it is saturated. The third there is the isotherms that are part of the chart itself. And then the fourth one are the mixing ratios, which are also part of the chart itself. And those last two kind of give an indication of basically how the dew point and the temperatures are plotted on the chart. Just another, this kind of a reference slide, not really anything I will talk on, but it's just another look at all the different lines on those charts and some of the sounding parameters that you can glean from those, along with an actual environmental sounding plotted on that. So just pause this if you wish and take a long look at the different lines and what they represent. All right, now let's start talking about how we can use these soundings to our advantage. And here we're talking about stability, and when we're talking about convection, we're looking for unstable air masses or an environment which promotes upward motion. And so we look at basically lapse rates to determine that. So for an absolutely unstable environment, we're looking where that red line is, a very quick cooling as you move away from the surface. So we call that a very steep lapse rate. So the environment is getting rapidly cooler as you move up away from the Earth's surface. A parcel cools at a certain fixed rate, but the environment changes daily and hourly actually. So when you see that steep, and that's what we see at the bottom of our soundings in the heat of the our environment, our summer and our springs, we get those super adiabats down low near the Earth's surface, and we see a very unstable low levels. So for absolutely stable, there in the blue, we're looking at an environment which cools very slowly with height, or might even actually warm with height, meaning an inversion. That's when you have an environment that will typically be warmer than any kind of parcel that's moving up, and so that parcel won't be able to continue upward motion, meaning that it will settle back down or not, or at least resist upward motion, so that'll be stable. And then you get the conditionally unstable environment where the environment basically follows both the dry, or in between the dry and the moist adiabatic cooling rates with height, meaning that a parcel, as it moves up, will be cooling at about the same rate as the environment it's rising up through, which means it won't have a whole lot of instability for a whole lot of strong upward motion, but with the right conditions, it can move up, or it could just stay where you put it. If it goes over a mountain, it could just stay at that new height. All right, so let's kind of make a determination between what the environment and what the parcel is. So when you're looking at a sounding, you're looking at the winds on that sounding, the temperature on that sounding, and the dew point trace. So those three traces are what defines the environment at the time that balloon was released and that radiosonde took its measurements of the environment. So it's a snapshot of the air mass for that day, and it gives you the thermal and the moisture profiles and then the motion characteristics with the wind. And so that's the environment. So when you're looking at a sounding and looking at those three things, the winds, the temperature, and the dew points, you're looking at the environment. So then what you do is you assume that there's going to be a parcel that may be lifted, and then it will always follow the dry adiabat on the chart if it's not saturated. And then once it becomes saturated, it will then follow the moist adiabats. And the difference between the two is when you got a dry air mass, it cools quicker than a saturated air mass, and so that's the difference in the two lines. There's different rates of cooling between the dry adiabatic lapse rate and the moist adiabatic lapse rate. So you follow that yellow trace there on the chart from the surface temperature, and then you find out where it hits the level of free convection. That's when it becomes saturated, and then you follow the moist beyond that upward, and you just compare it to the actual environmental temperature trace on the sounding. If that parcel happens to be to the right of it, then that means its temperature is warmer than the environment, which means it will promote more upward motion. So we're just looking at those two things basically to determine whether we have a propensity for upward motion with any parcel that might be lifted from the surface or from the low levels. So there's a lot of important parameters, levels that we look at, indices, and etc. on these, and so we'll take a look at some of those right now. So this is what you're looking at is a sounding that you would see on AWIPs, and so that's something that we'll be familiar looking at. But we'll look at some of these indices and parameters before we move too far on. So here we're looking at the lifted condensation level and the level of free convection. And so how do we compute, figure out what those would be? A lot of times those are on the charts for us. But if they're not, a good way to figure them out is for the LCL, the lifted condensation level, you basically just start at the surface dew point, the surface temperature, and you follow both the dry adiabatic and the mixing ratio lines until they meet. So you find that point when they meet, and that's your lifted condensation level. That's the level at which, once you lift that surface parcel, it becomes saturated at that point. And that's the LCL. And then if you want to find the level of free convection, so it may not still want to lift at this point. So you got to find the level at which it will want to lift freely through the atmosphere. So you got to find that point where the temperature of the parcel is equal to or slightly warmer than the environment. So you take that parcel that you lifted to the LCL and lift it until it crosses the environmental temperature trace, which is done right there. At that point, the parcel is at the same temperature and will continue to warm above the environmental temperature as it lifts further. So that's your level of free convection. You get a parcel up to there, and it's going to continue to move up until it reaches a warm layer in the environment. So let's move on now to the convective condensation level and the convective temperature. The convective condensation level, you just simply follow the surface dew point up the mixing ratio until you hit the temperature profile of the environment, and that's it. It's that simple. That's the convective condensation level. That's where you're going to see your cloud bases in general. If you get to that, and then if you want to know the convective temperature at which you'll start to see that formation of those convective cumulative clouds, you just follow that dry from that point of the CCL. You just follow down the dry adiabat to the surface and read the temperature at that point, and that'll give you the convective temperature, and that's useful later in the day because that kind of gives you an idea of what time of the day you're going to hit that temperature. And so you'll know kind of when to start expecting the development of cumulus and towering cumulus if you have the moisture available. All right, this is kind of just a review of the 4 levels that we just found in the convective temperature. Nothing I'm going to spend any time on, but just something for you to see. It's kind of more of a reference. It's easier. It separates them all together, and you can kind of see the starting and finishing points and the methodology of how you would find each of those layers or levels. So now let's start talking about energy, and energy is basically everything when it comes to thunderstorms, whether you have it or don't. And when we say energy, we mean the energy to promote lift, or the resistance to promote lift. So when we're talking about CAPE, we're talking about a measure of instability, the buoyancy of a parcel that's being lifted. And that's an area, and on a chart, a Skew T chart, area is proportional to energy. And so here at the integrated area, we look at all the area where the parcel is warmer than the environment. And so we integrate from the level of free convection to the equilibrium level. And that's basically where the parcel becomes warmer than the environment, and then aloft where it becomes equal to and cooler than the environment. So we look at that area and we integrate that area to get the positive area. We find out when that parcel is warmer than the environment, and that is our CAPE. And that's kind of a measure of our buoyancy and how much upward motion and how strong it's going to be. Conversely, the SIN is a measure of stability. It's the convective inhibition, and also it is an integration, but it's from the level of free convection down towards the surface. Any point in time when you're trying to lift a parcel and it's on the left side of the environmental sounding, it indicates it's cooler, so it would not really want to be lifted unless something was forcing it. So it would be cooler than the environment, meaning that it would want to settle back down. It's considered a negative area and an inhibition to convective initiation. And just a couple other examples of that. This middle chart here shows that you can actually have some convective inhibition aloft. If you have a warm nose, maybe you get a subsidence inversion aloft. There can be another level of aloft that the parcel has to try to somehow get through, and maybe if it's got a strong enough buoyancy from below, it can push through it. Maybe it can't, and that would be a cap aloft that would keep storms from developing, and that happens here in the summer a lot if we have high pressure settle over us for an extended period of time. There is a way to kind of figure out what you think your updraft velocities will be by looking at CAPE, because as we said earlier, this integration of CAPE is basically proportional to energy. So the larger the CAPE, the more energy you have, so the stronger the rising motions will be. So you take that's potential energy, and if you convert that to kinetic energy with upward motion in the atmosphere, you can get the maximum speeds. And basically it's a very easy calculation. If you know your CAPE, it's basically the square root of twice the CAPE to get your maximum updraft velocities. And from a study, from some time ago with 242 individual strong and violent tornado cases, they looked at the CAPE numbers for each of those, and they found out that the sweet spot for CAPE for strong and violent tornadoes is somewhere between like 1,100 and 3,000 joules per kilogram of CAPE. So that's just something to keep in your mind when we're seeing days around here where the CAPE's above 1,000. Then other things being right, that's basically indicative of strong upward vertical motion and potential for severe, if not tornadoes, across the area. Shape of the CAPE makes a big difference, whether it be fat, short and fat, and tall and skinny is the two that you seem to get a lot. Sometimes you get tall and fat and you get huge amounts of CAPE, 4,000 to 5,000, almost off the scale. Looking at these two soundings, they both have the exact same CAPE values, but you can see that it's distributed much differently through the depth of the environment. On the left, it's a thin, narrow CAPE from top to bottom. On the right, it's a fat CAPE and it's shallower. So which one of these would have the better potential for severe weather? Well, the answer would be the fat CAPE. The fat CAPE is indicative of a bigger difference between the temperature of the parcel and the temperature of the environment, with the parcel being much warmer than the environment, which means it's going to have a stronger upward motion at any point in time through its ascent. The other thing is if you have the stronger CAPE down lower in the atmosphere, that also is better for the strong storm development. So we're always looking for a fatter, lower CAPE for severe and strong thunderstorm development. So of course, we've talked about the inhibition to upward motion, and when we're talking about thunderstorms, there's three primary ingredients that we look for, that we need to basically bake the cake, so to speak. And the first one is moisture. Pretty self-evident. You got to have the moisture. You can have all the instability in the world, all the CAPE in the world, well, all the instability and upward motion, but if you don't have moisture, you're not even going to have clouds, much less a thunderstorm. The second thing you need is the instability itself. So you need the rising motions, and then you need the moisture they're associated with. Those are really the two ingredients you need for a thunderstorm, but the third thing that you need to initiate a thunderstorm is a trigger. And so with the triggers around here, you typically don't get a lot of thunderstorm activity just by heating the surface of the earth. You need something else to force that, to trigger, initiate that upward motion. For us, this time of year in the spring, it's often the dry line and the convergence along it. Any other kind of front, maybe we get a backdoor late season front that would come in, that would also be a lifting mechanism. Something that we get almost daily in the monsoon season is gust fronts from other thunderstorms, from eroding, dissipating thunderstorms, mainly up in the mountains. They send out the outflow gust fronts, which tend to initiate new convection on them. And then earlier in the day, we always get the mountain storms. That's the orographic upward lift that pretty much starts the thunderstorm day, followed by the gust fronts later in the day. So now let's start talking about some of the indices, and we'll start out with the one that we're probably the most familiar with and we use pretty religiously is the lifted indice. Extra credit if you can tell me how it's calculated, because I'll be honest with you, I knew a negative number meant unstable. I knew a positive number meant stable, but I really didn't know what that number was, to be honest with you. And I might have been the only one in the office, but you start at, you take a surface average in about 50 millibars of the temperature and the dew point, and you lift that parcel up the dry adiabat and the mixing ratio to the LCL, and from that point up moist adiabatically until you get to 500 millibars. At that point, you compare the environmental temperature trace to what the parcel would be. And so it looks like this as far as an equation is. It's basically just the 500 millibar environmental temperature minus the 500 millibar parcel temperature. And if the number is negative, that means the parcel is warmer than the environment, which means it's buoyant and would want to rise. So that's basically lifted indice in a nutshell. It's very simple. It starts out pretty close to the surface, and you just lift it up to 500 millibars and see if that parcel at that level is unstable or not. And just some quick numbers to go by, for LIs. If it's positive, it's stable. If it's a low negative number, you just have marginal instability. But the higher that number gets, the more extreme that instability becomes, and the more likely you are to get a stronger thunderstorm. So we go into the K index that we like to look at a lot too. Employs three variables basically. It looks at the lapse rate, looks at the moisture content of the lower atmosphere, and the vertical content. How deep is that moisture? And so it looks like this as far as the equation is concerned. It looks at the lapse rate, the low level moisture, and the dew point by looking at 850, 700, and 500 levels. And these are some of the numbers that they mean. The larger this number is, the more likely you are to be seeing thunderstorms across the area. And then we look at the total totals. For us, we're west of the Rockies, so we look at those numbers on the left side of the chart. But total totals is a combination of the vertical totals and the cross totals. The vertical totals is basically just the difference in temperature between 850 and 500. It's basically a lapse rate. And the cross totals looks at the moisture at 850 with the dew points and subtracts it from the temperature at 500 millibars. And I'm not real clear on what the thinking is on that and what it does for us. But if you look right here on the chart to the left, the cross totals with the moisture content, if you're below 28, thunderstorms are unlikely. But once you get above that, you start seeing increasing levels of thunderstorms. Then on the total on the right-hand side there, west of the Rockies, you can see there's a bunch of overlap between that. But we're always kind of looking for right around 50 or higher to get the thunderstorms across our area for the most part. Now let's talk about shear. We'll take a turn into the shear here. And of course, there's two kinds of shear. They're both vertical in nature, but you get the speed shear and you get the directional shear. So the change in speed with height and the change in direction of the winds with height. And if you look in this blue chart here on the left-hand side, you can see you don't have any organization, either in speed, it's up and down and up and down. In direction, it's all over the place. And so this is what we call unorganized, no speed shear, no directional shear of any significance. And so you get these unorganized single cell, multi-cell storms. We seem to get that a lot in our summertime. Then on the right-hand side, where you have organized convection, you have the speed shear on the left here, increasing, not a whole lot of directional shear, but a whole lot of speed shear. You get the multi-cells and the squall lines. Now on the right-hand side, you see you get both. You got a lot of directional shear, a lot of speed shear, and that's when you get your supercells. So, to break it down, you get four different possibilities with shear. You can have very weak speed and directional shear, and that's when you just get your air mass storms. Severe weather is not likely unless it's pulse severe, just real brief, maybe mostly moderate sized hail and a little bit of wind, but not much more than that, because these cells are usually short-lived and don't really get all that strong. Then if you have the strong speed shear, but the directional shear is weak, that's when you start to get more organization, you get longer lived storms, you get more of those MCSs, which develop into lines. That's when you get your hail, some weak tornadoes are possible, and possible heavy rainfall. Then if you go down to the weak shear, that's speed, the weak speed shear, but strong directional shear. If you don't have speed shear, you're pretty much just going to have the general air mass storms with severe weather, not likely, and just a pulse severe here and there, but nothing really organized. So again, you're back to more short-lived type environmental storms. Then finally, you have the case where you have both strong speed and directional shear. In that case, that's where your supercells tend to form with large hail, strong tornadoes, and heavy rain possible. So this is just a chart that shows the correlation, the relationship between CAPE and shear. If you got strong shear and high CAPE, you're in the supercell category. If you've got really weak shear, no matter the CAPE, you're predominantly in the ordinary storm cells. Then if you get a mix of the two, that's where you get the full range, anywhere from some ordinary storms to some supercells. So now let's talk about some operational aids real quick with soundings. And this is from our Google Sites page here at EPZ. You click on the Mesoanalyst dashboard here on the DSS tab. And from there, you'll go to the severe weather checklist. And from that severe weather checklist, you get all these different checklists for the different types of storm, like whether it be flash flood, hail, tornado, downburst, all that kind of stuff. These are the checklists that you can use to go along with looking at the soundings. And so here's just another look back at some of those different indices and some of the numbers and what they mean. Just for your, I'm not going to go through this by any means, but just to have it here as a reference. You can stop and look at it now, or look at it, refer to it later when you're working radar if you wish to, or you can do a screenshot of this. This is not hard, for sure kind of things. It's kind of like rule of thumb numbers. But it's kind of a cheat sheet that you can use to see what kind of day to expect based on some of the stability parameters that you're seeing on the sound. So let's talk about working one of our soundings with a tornado. So we're looking at tornadoes. There's our checklist there on the left. This is an actual tornado near Deming in 2006. And then we had another one, White Sands Missile Range, in 2007. So when we're looking at tornado potential, we're looking at shear, helicity, CAPE, and how low the LCL may be. So here's a sounding from October 10th of 2006. And so let's go through the checklist real quick. And the first thing, we'll start out with the shear. The shear on this one from 0 to 6, from ground to 6, was 68. If you look on the checklist, that meets both the greater than 20 and then greater than 40 knots. So we get 2 checks there. And we look at the storm relative helicity from surface to 1 kilometer. We get 313, and so we're over that 200. We get another check. So let's look at the CAPE. We're at 1754, so that gives us another check on the 1,000, but we don't meet the 3, so we get one more check. And we tend to look at the LCL. That's at almost 1.2 kilometers, and so that does fall below this 1.4 kilometers, so we get another check. We don't get the second check there. It's not that low. And so we get 1, 2, 3, 4, 5 different check marks, and that puts us in this box here. It says expect an isolated F2 or stronger tornado. So it worked out that day. It's not always going to work out. There's going to be a lot of false positives and some negative, it doesn't work out. But we had some other hints on this one. We had a SIG-TOR light up a little bit in a couple of different places for hail and tornado there. So this sounding on this afternoon gave us indication. This was from El Paso. This was in Deming, about 65 miles away. So the environment looked like it was ripe for it, and you can just look visually at the wind profile there. You can see there is some turning with height, so you got a little bit of directional shear, and you do have some speed increases with height. So you had the right kinds of shear too. It just looked right. So now let's go to flash flood. So with flash flood here, again, we pull up the flash flood checklist and we have a sounding here. And so let's compare what we have. So 1.6 PW, so that meets the over 1 and over 1.3 PWs on the checklist. That gives us 2 checks. And we look at the RH at the lower levels, and we see that we got 94%. So it's a really moist, and you can just see by looking at the dew point trace being right up against the temperature trace, so you get to 500 millibars. That's a deep, moist sounding there that you're looking at. Then we look at the CAPE. We see that we have 1200 plus CAPE, and so that gives us 2 more check marks on the checklist. And then we look at the storm relative velocity of 72. So that doesn't give us our 200, but then we go over to the storm relative winds and stuff like that. And we see that they're below the 25 knots and below the 20 knots of steering flow. So we see that, and if you look at the profile of the winds, the wind barbs, you can see they're not real strong winds. So here we get 1, 2, 3, 4, 5, 6 different check marks, 7, because we got the upslope flow. So let's talk about that. And that's not on the sounding course, but we know we've got the Sky Islands, we've got the Franklin Mountains. So we know we're going to have the upslope flow, which would initiate the lift. So and so that gives us enough, that we would consider that to be a flash flood potential kind of day. So let's look at these 2 soundings and do the same thing. 1.45 and 1.71, that gives us 2 check marks on these 2 days. And this is basically August 1st of 2006. And we'll show you what happened here in just a second on that day. Then we go to our moisture, and we definitely have really high levels of moisture. You can see it's a deep, moist sounding just by looking at the dew point trace, but you also look at the RH at mid and low levels. You can see those high numbers there. Then we look at the CAPEs, and we're right around 1,000 in both days, so we get that check mark. And then you look at the motions, and the motions are definitely below that 20 to 25 knots. So we're looking at fairly slow storm motion. Then we got the upslope flow again. So again, there's 7 more check marks, and so that gives us another potential day for flash flooding. And this is what the El Paso Times happened to have those 2 days. This is August 1st and 2nd, where we had what they called historic crippling type torrential downpours and flooding across not just El Paso, but other parts of the area. Hatch was inundated pretty badly too, and Canutillo, the lower valley. I mean, there was just a lot of heavy duty rain that fell. Here's some of the pictures captured from that day. So again, the sounds worked out pretty well. So here we are on the convective side of things. Again, looking at hail on this day. So this is now 2009, September 17th. And we'll go through the checklist looking for severe hail that's larger than 1 inch. We start out looking at the shear. We've got 43 there from surface to 6 kilometers, and that gives us 2 check marks on the checklist. Look at the PW, definitely above 0.6 and 0.9, so we get 2 more check points there on the PW at over 1 inch. And we look at the moist, the Mu CAPE, the most unstable CAPE is definitely over 1,000 there, so we get another one. We don't get the 2,000, so we're only at 1,360, but we get another check mark for CAPE. And then you look at the wet bulb 0. It's actually not low enough to give us a check, but it's still relatively low for our area because we're usually so high base and everything on that. So that gives us enough check marks that it puts us down here where it says expect a few to scattered severe storms may occur with max hail size up to 1 3/4 inch. And if you look over here in the bottom, we also had a little bit of signature there with SIG hail on both of the things. So we had some indication with this that there was potential for hail. And there's a cross section of a storm that day, and there's some hail damage that was produced. Now let's talk about microburst. That's something we get around here pretty commonly. Which one of these would be a dry, and which one of these would be a wet microburst? Give you a second on that. And I think that's pretty obvious. I think all of us would get that right. The one on the left with the dry low levels would be the dry microburst. The one on the right with the really moist low levels would be the wet. And that's kind of the schematic of how it's formed and what it looks like. We actually have a dry microburst checklist. So, moist aloft with evaporative potential down below. The high storm base allows for, accelerating downward winds for a microburst or downdraft. And then on the right-hand side here with the wet, you're entraining some of this dry air, and this evaporation aloft will cool that air and accelerate it down towards the surface through this moist. And as it does, it collects the rainfall and really produces very heavy rain in many cases. So on the left, you're looking for that inverted V with dry low levels, moist mid levels, and a very high convective cloud layer. On the right-hand side, so you get all green checks when you're looking for all these things. You'll get all good check marks on the checklist. On the right-hand side, it more looks like a capital Y. Your moisture is down low, your dry air is up high, and your CCL is really low, which helps you get the heavy rain. So let's look at a downburst parameter sounding and the checklist that we have here. This is, if you notice, this doesn't look very much like either of the ones that we saw before, and we consider this a hybrid. Look at the surface. This is a 0Z sounding, and you're seeing a inversion. You're seeing a moisture and a coolness at a very shallow depth. And what happened on this day is this sounding was released after the event occurred, and so it did contaminate the lowest levels of the environment. And if you were to put this back up to the max temperature of the day and the low dew point before it happened, you'd get a 40 degrees difference, dew point depression at the surface. And your mean layer RH should be near 60 or below. We're right at 60, and is after the event, so it probably got bumped up a bit. You can see the lower RHs in the 30s. So we probably do get this green check easily before the event happened. Then you look at the D cape. The downdraft cape is at 1650, so that gives you a couple of check marks there for the cape being over 500 and 1,000. Then you look at these winds here, and you see these winds are light, so they really don't meet the criteria for these strong winds aloft. So we don't get check marks there, so that doesn't work out in our favor. But look at the cape, and we got big cape here. It's 2950 almost. So we get two checks for above 1,000, above 2,000. Then we look at PW lastly. You got 1 1/4 inch PW, which easily meets the 0.9. So here we are with 6 check marks, which gives us a few severe downdrafts possible. And this is what it looked like that day over EPZ. This is the infamous hybrid wet type microburst that landed right on top of the office. I think it gave us over 1 inch of rain. And look at these winds, 73 mile per hour wind gust with that. And you can see over here with the winds, you can see the wind spike up high. You can see the RH spike very high, and the temperature dropped real quickly as that descended upon the office. So that worked out. So we're going to end it here. I've gone long enough with that. I thought it might be helpful to see how the checklist and the soundings can work together to help you kind of get situational awareness on what to expect for the day. This is just scratching the surface, right? So don't stop here. If you're really interested in getting better at reading soundings and knowing what kind of weather to expect based on what you're seeing there, train up. The CLC has a lot of really nice courses, and I can help you find those courses to help you kind of expand your ability to read these and understand them and know what to expect. That's it, and thank you very much. I appreciate you.